Today we're going to talk about Kramer's rule, and Kramer's rule is a way to solve linear systems, particularly 2 by 2 and 3 by 3s, that sometimes can be a whole lot easier than doing either substitution or elimination in the normal way. So I'm actually going to go all the way to page 60, let's see, to exercise 423. So I'm going to go to page 69, all right? So, and I'm going to talk about this problem because they do a lot of explanation that I think, honestly, is hard to understand without any background, right? So I'm just going to do one example for you. And I'm going to do a couple of examples so you can see them. But here's how this works. All right, so when you have Kramer's rule, the first thing you're going to do here is you're going to write an augmented matrix, right? Where I'm going to line up all the x values here, the y values second, and then the solutions third. So I'm going to write this as -2, 1, because remember there's a 1y right there. And I'm going to write a 1 here and a 3. And then I'm going to draw this vertical line, and on the right side, I'm going to write what the solutions would be. Or not the solutions, that would be the wrong thing, but just what these linear equations are equal to, I should say. All right, so the first thing we're going to do is we're going to find the determinant, and this is the determinant that they're talking about, okay? So that determinant, that's what they call D, right? So I'm going to write it exactly like what we did a couple of lessons ago. I'm going to write -2, 1, 1, 3. Remember those vertical lines around the matrix, that is telling you that this is going to be a determinant. So you remember you're going to multiply those two together, and then you're going to subtract these two numbers, okay? So we have -2, I'm going to zoom in so you can see a little better, hopefully, times 3 minus 1 times 1, okay? And if you do the math there, right, you end up with -6 minus 1, so you end up with a -7, all right? So that's what we're going to do first. And then now we're going to do that. There's nothing different so far. What we're going to do next is we're going to find the determinant of x. And to find the determinant of x, all right, what we're going to do here, what numbers are we going to put in here? That should be the question you have. So what we're going to do, and it's a little bit weird, right? So again, don't erase any of this. All right, but essentially what I'm doing, let's see if I can do it with this. I am essentially removing these right here. I'm moving those out of the way, right? And I'm replacing those with this 5 and this 7 that are right here. Again, I'm going to replace that. I'm going to put it right here, okay? So let me actually draw it for you. And that's the reason I actually wrote that column in red, so you could see how I was moving things. So I'm going to write that 5, 7 right there. And then we have a 1 and a 3. Okay, so that you notice what happened. Again, I replaced this column with this column. All right. And now we're going to do the determinant like we normally would, right? We're going to multiply these two numbers together and then subtract these two numbers. All right, so that would be, let's see, 5 times 3 is 15, and then 7 times 1 is 7, so we have 15 minus 7, which is going to be 8, right? So this is going to be equal to 8. So the determinant of x is 8, which is what they have right here. Okay, now finally we're going to find the determinant of y. Right, so the determinant of y, kind of similarly, or the same logic as what we just did, except for now, we are going to replace this column right here with this 5 and this 7. All right, so we're going to replace it with that. So that's how this works right here. So we have, excuse me, change colors there. We have -2, 1, and then we're going to end up with a 5 and a 7 here. Okay. So let's do the determinant for that. So we end up with, let's see, -2 times a 7. So that's going to give us a -14. And then we subtract this 5 times this 1, which is going to give us a 5. So we end up with a -19. Okay? And then finally the answer, and that's what they're writing here. All right, so I'm going to write it in perhaps a way that you can figure out what they're doing, is to figure out the x value, all right, which would be our solution. We're going to divide the determinant of x over the determinant, which for us, the determinant of x was 8. And then the total determinant was 7, I believe. -7. Okay. Well, hold on. This was +8. My bad. +8 over -7, which is what I have right here. And then y is going to be equal to the determinant of y over the determinant, which is going to be 19 over 7. So that's how I got this answer. Now, notice that the advantage of using Cramer's rule is that if I were to do this with substitution or elimination for that matter, I would end up with some pretty ugly fractions, all right? So Cramer's rule really helps you to get around all of that. All right, so I'm going to quickly talk about what would happen. So this is going to be a pretty short lesson. So sometimes, all right, so we're going to look at a problem here. And let's see, I don't know if I took this problem. Let me see if I took it from somewhere here. No, I don't know where I took this problem from, but it's a good example nonetheless. So this is going to explain. So I'm kind of backtracking to page 68. So what could happen, let's say that you had something like this, okay? So this is an example of when you would have infinitely many solutions. Let's say that you have a 3x plus 2y, and that's going to be equal to 5. Now let's say that you have a 6x plus 4y, and that's equal to 10. All right, what we're going to do now is we're going to do Cramer's rule to figure out this answer. So let's do it one more time. Let's see if you remember how. We're going to start off by writing the augmented matrix part. And I'm going to write this in red. You don't have to necessarily use a different color, but I normally like to do that, especially when showing you how to do it. So we're going to start off with the determinant, the total determinant, which is going to be, we're not changing anything, it's just these 4 numbers right there. All right, so we have a 3, 2, a 6, and a 4. And if you do the determinant, you'll see that if I do the determinant, I'm going to end up with a 0. Okay, if I do 3 times 4, which is 12, minus 2 times 6, which is 0. So we end up with 12 minus 12 here. All right, now the determinant of x would be, remember, we would replace, for the determinant of x, we would replace this column right here with this column. Okay, so we're going to write this as 5 and 10, and then 2 and 4, and we're going to do the determinant. 5 times 4 is going to be equal to 20, and then 2 times 10 is also 20, so we end up with a 0. Okay, and then finally, the determinant of y, that's what we replace this column right here with this column. Okay. So we're going to write a 3 and a 6, and we're going to replace the y column with a 5 and a 10. Now again, if you do the determinant, you'll find out that you end up with 30 minus 30, which is also 0. So this is the important thing for you to know. If all of your determinants, and I mean all of your determinants, are equal to 0, okay, and that's what this is saying, then you're going to have, remember, x would be dx over d, and y would be dy, which is the determinant of y over d. This is basically all zeros. If you happen to have that, then you're going to have an infinite amount of solutions. Again, only if all your determinants are 0. Okay? Only if that happens. Every single one of them is 0. Now, if instead, and this is what happens here, if your determinant would have been 0, for example, but let's say dx would have been like, say, 5, and dy would have been, I don't know, let's say 2, then that means that you have no solution. And be careful, if if this number is anything other than 0, but you have zeros everywhere else, you are going to get a solution, all right? So I know that's kind of confusing, but make sure you read exactly what I'm saying. If all your determinants are 0, you have infinite solutions. If only this determinant, which is normally the determinant I was talking about here, is 0, but then nothing else is 0, then you're going to have no solution, okay? So again, all of them have to be equal to 0 to have infinite. Well, without further ado, to not make this video very long, that's essentially how you use Cramer's rule. I'm going to set up a Delta Math assignment, so make sure you take a look at it, and that'll be due on Monday. All right, until next time.